Okay, so this is the kinetics review. Please make sure you have your reference tables. Maybe you look over your notes, etc. first before we get into this. Okay, as the temperature of a chemical reaction in the gas phase is increased, the rate of the reaction increases because, well, if you think about gases, you increase the temperature, gas particles are going to move around, they're going to collide with each other in the sides of the container more often. So it would not be fewer. Would it be more? I'm guessing yes. We would not necessarily have more activation increases, activation energy, and concentration. We're not adding more. We're just going to have better particle collisions because they're moving around. What is required for a chemical reaction to occur? Standard temperature and pressure, a catalyst, effective collisions, equal number of moles. The only one that you absolutely need are effective collisions. You could be at standard temperature and pressure. You could have a catalyst. You could have equal number of moles, but you don't need them every time. Two reactant particles collide with proper orientation. This collision will be effective if the particles have high activation energy, high ionization energy, sufficient kinetic energy, sufficient potential energy. So this is punching a window. If you want to break a window, which I don't recommend, ask for help, then you would need to have the orientation, which you have. You need to orient your fist with the window. The other thing you would need, if I need to break that window with my fist, I need enough energy. I need kinetic energy, energy of motion, not activation energy or ionization, which, by the way, ionization energy is the energy required to remove electrons, not what we're talking about here. And not potential energy either. Storing energy, nope. In each of the 4 beakers shown below, a 2 centimeter strip of magnesium ribbon reacts with 100 milliliters of HCl, that's hydrochloric acid, AQ, under the conditions below. So you've got molarity, which is concentration, and you've got temperatures, which will happen at the fastest rate. So remember, you want the most effective particle collisions, which is going to happen if you have the most particles to begin with, which would be higher molarity, 1 molar versus 0.1 molar. And if you have a higher temperature, you're going to have more collisions, which means you need D, which is per. Okay. Given the reaction, if the concentration of HCl is increased, the frequency of reacting collisions will. Okay, so we're going to increase this. If you have more, you're not going to have fewer collisions. You're going to have more. So if we have more concentrations, we're going to have an increase of reactant collisions, producing a decrease in reaction rate. No, if you have more collisions, you're going to increase the rate of reaction, make it happen faster. That's why we want it to happen. When a single 1 gram piece of zinc is added to 3 molar hydrochloric acid at 25 degrees Celsius, the reaction is slow. Which procedure would most likely increase the rate of the reaction? So we have a piece of zinc using 1 gram of powdered zinc. That could do it because that would increase the surface area, making there be more reaction between the reactant particles. Using 1 molar hydrochloric acid. Well, we already have 3. Making it less concentrated is not going to speed it up. Decreasing temperature is going to be fewer particle collisions. Decreasing the concentration of zinc, no. So we're going to use that one. As the surface area of the zinc, so this is probably what we're talking about here, going from a solid chunk to maybe solid powder, which, by the way, powder is still a solid. If you increase the surface area, the rate of the reaction will also increase, okay? Because that means that all of the zinc particle is touching all of the HCl a lot more quickly. What does a catalyst do? A catalyst speeds up the rate of the reaction by lowering the activation energy and providing an alternate reaction pathway. That's just a definition that I can spit back at you. It is no. It is not an additional reactant because it doesn't participate in the reaction. It limits the amount. No. Changes the products. No. It just is a shortcut. It gets you there faster by lowering the it's like a shortcut. If a catalyst is added at equilibrium, what does that mean? Well, at equilibrium, you have a forward reaction and a reverse reaction. So if you have temperature and pressure remaining constant, what is going to happen? There will be, oh, okay, I need to reread this. See, I thought I knew the question, but I got to read it again. If a catalyst is added to a system at equilibrium and temperature and pressure remain constant, there will be no effect on the rate of the forward. Well, there will be an effect on the forward because it will go faster. There will be an effect of the rate of the reverse because it will happen faster. Activation energy, heat of reaction. So activation energy will be lowered, and the heat of reaction, that won't change. So 3. And by the way, if you are looking at the PE diagram, that would be exothermic. If you have a catalyst, this will stay the same. This will stay the same. But instead of going all the way up here and down, you're just going to boop, which means this is your activation energy with a catalyst. This is without. That's a lot less. But what is delta H, or the heat of reaction? That's the difference between the reactants and products. And notice that doesn't change. That's delta H. Right. Which freezing is exothermic? Which change is exothermic? Exothermic means giving off of heat. So solid to liquid to gas. That is gaining energy. That would be endo. Because if you have snow and you make it liquid water, you have to take in heat, liquid water to make it gaseous steam. That would be bringing in heat. However, gas to liquid to solid is exo. So which of these is a phase change going either from gas to liquid, liquid to solid, or gas to solid? Freezing of water. Freezing is liquid to solid, and right there is my answer. Vaporization means to form a vapor, so liquid to gas. Sublimation, that's solid straight to the gas phase. For a chemical reaction, the difference between the PE of products and the PE of reactants, we just talked about that over here. That's called the heat of reaction. Heat of fusion is a constant we use during the either solid to liquid, which is melting, or liquid to solid, which is freezing. So that's not it. Which sample has the lowest average kinetic energy? This is code for temperature. So we don't care about grams. Which is the lowest temperature is choice 4. Okay. The heat of, we just did this. The heat of reaction is equal to the PE of products minus PE of reactants. It's always final minus initial. So the final is the products, the initial is the reactants. According to table I, which means I need to get that out, which equation represents a, there should be a space there, which equation represents a change resulting in the greatest quantity of energy release? So by the way, energy release means negative delta H. So these better be negative. So I'm looking for that first one. 2C plus 3H2 yields C2H6. Okay, so that's like about halfway down. So that's negative 84.0 kilojoules. C2H4, that is positive. So that's already not our answer because it was taking heat in. Hager process, that's negative 91.8. Okay, so that's looking like our answer so far. Let's just double check the last one. N2 plus O2 is 2NO. And be careful because some of these are super close. The one below it, the only difference, we've got 2 oxygens and then NO2. Yeah, so some of these reactions are really similar, so be careful. But this one is positive, so that's not our answer. So out of our 2 negatives, we want the one that is the bigger one. Okay. All right, back to the top. What does nature want? Nature wants higher entropy, lower energy. Think about if you don't mow your lawn all summer, it's going to be all over, grass and weeds just growing all over the place. But you have put no energy in, and that's what nature wants. Lower energy, higher entropy. That is choice 1. All right, which increases disorder? So we need to look at our phases. Solid to gas, that's probably our answer. Gas to solid, nope. Solids to solids, gases to liquids, nope. So there it is. Given the diagram representing a closed system at constant temperature, so that's important, it's got to be closed. What's occurring at equilibrium? So notice what this is. This is the same substance in different phases. This is called phase equilibrium. So let's talk about it. So you've got something happening this way, which is liquid to gas. Liquid to gas would be vaporization or evaporation. And gas to liquid would be condensation. So when we're talking about equilibrium, we're talking about rates being equal, concentrations being constant. So masses are not equal, volumes are not equal. Look, there's not as much gas as there is liquid, so those are not equal. Number of moles, the coefficients of both of those are 1, so that's not it. You could do GFM. No, it's not going to do it. It's a constant temperature. We don't know that it's at STP, so you can't necessarily use 22.4 liters. I know that. So the rate of evaporation equals the rate of condensation. Okay, let's continue. Which two factors must be equal? So our code is re-equal, which means rates, and con, which means concentrations are constant. Concentration of reactants and the concentration of products are equal. Con, not equal. Number of reactant particles are not equal. Rate of the forward and rate of the reverse, that's our answer. Re-equal, rates are equal. Solution equilibrium. Okay, so this is another definition. Solution equilibrium must be saturated, which means you're at the maximum. You can't take any more in or get rid of any more. It's the maximum. So if you were to try to dissolve more, the amount that you dissolve would be the same as the amount that comes out as a precipitate. So saturated. Okay, so we've got, looks like phase equilibrium here. It's H2O, although that looks like a 0. Anyways, solid to liquid, liquid to solid. Now you might remember phase change diagram. Where is that phase change? It's here, and I've always drawn it this way. So this phase equilibrium occurs at what temperature? What temperature does solid H2O or ice melt and that liquid water goes back and freezes? So that's 0. Look at how naughty they are. They tried to include 32. That's 32 Fahrenheit, which is the F words. We don't use that. So now we just went down to these. Is it 0 Kelvin or is it 0 degrees Celsius? And hopefully you know that it's 0 degrees Celsius. 0 Kelvin, that is absolute 0, which is no particle motion. So nobody's there to measure that. Okay, so we've got equilibrium. See that double-sided arrow? Which favors the reverse. And by the way, reverse would be going from the right to the left. So which change favors going that way? So with Le Chatelier's principle, you need to know if there's too much, shift away. So if you're full from dinner and somebody gives you a plate, you shift it away from you. You can't eat anymore. And that's so hard to read. I apologize. If there's not enough, you're still hungry, you're going to shift that plate of food towards you. So that's the phraseology you need. Too much, shift away. Not enough, shift towards. So if you want to favor going back, decreasing HI. If you decrease that, that means not enough, you would shift towards. So that means that's going to the right, which is the forward reaction, which means no. Temperature is over here at heat. So if you decrease that, we're going to shift towards, hey, that's the reverse reaction. That's probably our answer, but let's just double check the other two. Increasing concentration of I2. If this goes up, too much, shift away. That's going into the forward, so that's not our answer. And increasing pressure. So remember, with pressure, you need to have the gas phase, which we do. You need to have unequal numbers of moles. So this side has a coefficient of 2, which means 2 moles. This is a coefficient, nothing written, so that's a 1. This is a coefficient, nothing written, which is 1. So this side is 2 moles. This side is 2 moles, which means that pressure is not a stress in this case. So our answer is indeed choice 2. And I missed 21 entirely. Oops. The temperature at which solid and liquid phases of matter exist at equilibrium. Oh, we just talked about this. So this is the melting point. So that is solid to liquid. Melting point is also the same as the freezing point, but you see that that is not an option. Up here, system at equilibrium, which will be the result of an increase of temperature. So temperature is here. Too much, shift away. So we're going to shift to the right. So we're going to get rid of those. And as we shift to the right, anything that the reaction arrow points to will increase. And anything that it does not point to, it points away from, will go down. So equilibrium will shift to the right, and the concentration of NO2 will decrease? No, it will increase. Choice 4. Another equilibrium called the Hager process, which occurs when the concentration of H2 is increased. So too much, shift away. If you shift away from the increase, that means this goes up, this goes down. Equilibrium shifts to the left, no. Shift to the right, and N2 decreases. Choice 3. All right, how's it going? 25. Again, we have the Hager process. Which change will cause the shift to the right? Decreasing H2? No, because that would be not enough. Shift toward, so that's not it. Pressure. We do have gas phase. We do have unequal number of moles because this is a 1 plus 3 is 4 and 2. So remember, and this is something that you have to remember, if you have an increase of pressure, you go from the side with more moles to fewer. So that would be a shift to the, but that's a decrease in pressure, so that's the other way. Increase of pressure goes from more moles to fewer, which is to the right. Decrease of pressure would go from fewer moles to more, which is to the left. And that's, see, the devil's in the details. Increasing the concentration of N2, which means too much, shift away, that's to the right. That could be, that's our answer, because energy, if you increase that, we're going to shift to the left. So it's got to be choice 3. Now you get to hear what it sounds like in my head every time I do multiple choice. Again, Hager process. What occurs when concentration of H2 is increased? Too much, shift away. I don't even know what these say yet. I'm just going to figure it out. Too much, shift away. So this goes up, this goes up, this goes down. The rate of the forward increases, so yes. And the concentration of N2 decreases. That should be our answer. Let's just make sure. No, the forward is increasing because we're shifting right. The forward and the concentration of both increasing. No, N2 is going down. No, so it has to be 1, like we said. What will a catalyst do? Catalyst is going to get you there faster. It's going to increase the forward and the reverse equally. Why would you add something that has no effect? That's pointless. And it's not going to shift either one. It's going to do both. It is, again, this is the same question. Addition of a catalyst will increase the rate of both. Which will shift the equilibrium to the right? Increasing temp. Temp is here, so too much, shift away. That's going to go to the left. I'm going to skip pressure right now. Decreasing SO2. So if we decrease that, it's going to shift toward, so that's left. Decreasing O2. So you're going to shift left. So it's got to be pressure, but now let's prove it. So gas phase, we have it. 2 and 1, this is 3, this is 2. So if you increase pressure, you're going to shift from the side with more moles to fewer, which is this way, which is what they want. But the reason why I skipped it at first is because it just takes more thinking. So I just got rid of the other ones. Last one, pressure. First of all, we have gases. Yep. Do we have unequal number of moles? 4 plus 1 is 5. 2 plus 2 is 4. Yes, we do. If the pressure is increased, so we go from more to fewer, which means that way. If we go that way, this goes up, these go down because we're shifting away. So now the question says, what happens to Cl2? It will increase. Okay? Any questions, please reach out. Thank you. Take care.